is on the march. A mass migration is pouring into the 7 western states, eager to share in the industrial expansion of a region where people want to live. To keep pace with this tremendous growth, steel production on the West Coast is being steadily increased. For the first time in history, rich California iron ore deposits are being tapped and combined with high-quality Western coal to make steel. Just 45 miles east of Los Angeles, the West Coast's only integrated steel mill is bringing new industrial strength to the West. The manufacture of Western steel starts with iron ore produced in the company-owned Eagle Mountain Mine in the California desert near Indio. Because the ore body is located in an undeveloped area, the company built a 52-mile railroad across desert wastes to link it with the railroad main line. While American iron ore sources have been dwindling at an alarming rate, the development of this Eagle Mountain ore body ensures ample iron ore of high quality to supply the Kaiser Mill for more than 60 years. By scraping away the top earth and drilling into the rich ore body, the iron-bearing rock can be mined by the economical open pit method. Drill holes are charged with dynamite that breaks the ore so that huge shovels can load it into rugged dump trucks that haul it to the crushing plant nearby. A powerful jaw crusher breaks the ore to a size that can be conveniently handled, after which it is stockpiled or loaded directly into railroad cars. It takes only an overnight haul for the ore to reach the steel mill 160 miles away, one of the shortest iron ore hauls in the country. Back at the steel mill, each shipment of ore is spread evenly over long stockpiles. This ensures uniformity in analysis as the cross-section of the stockpile is removed and sent to the blast furnace. The other basic raw material in the production of steel is coal. This comes from the company-owned Sunnyside mines in central Utah. From here, miners send a continuous stream of coal to the mill, coal that makes strong coke and is rich in chemical byproducts. Working 3 miles back in the heart of a mountain, the miners use the safest types of modern equipment as they drill into the coal veins and charge them with explosives to blow out the black coal. Electrically powered machines gouging into the loose coal load a mine car in a minute, saving miners the back-breaking job of shoveling. Electrically driven, rubber-tired trucks haul the coal to the main shaft, where it is loaded mechanically into waiting mine cars. Every half hour, with clock-like regularity, electric engines pulling the mine cars emerge into the open. In addition to the Sunnyside mine, there are sufficient coal reserves in adjoining mountain ranges to supply the needs of the mill for more than 100 years to come. At the steel mill, the coal is mechanically crushed, blended, and pulverized before it is charged into the ovens to be made into high-quality coke. In the coke ovens, the coal is baked about 17 hours to drive off volatile matter. When the coal has been reduced to coke, it is pushed from the ovens by a gigantic ramrod. The coke is sealed within the oven by airtight doors and does not burn. If oxygen were present, the hot coke would consume itself. To preserve the physical and heating qualities, the coke is sent to a quenching station, where large sprays pour water on the glowing mass, and a cloud of steam billows into the sky. After the burning coke has been extinguished, the hot car dumps its load onto the coke wharf, where a workman sprays the last remaining embers. It is then conveyed to the blast furnace. Not all of the output of these 135 ovens is coke. Important is the volatile material carried off in the gas during the coking process. In the byproducts plant, these gases are processed into 9 basic chemicals from which many vital products can be made, ranging from synthetic rubber to high explosives. At the 2 blast furnaces, iron ore, coke, and limestone are mixed in accurate proportions and fed continuously into the top. The raw materials gradually descend in the furnace, meeting at the same time a blast of hot air and gases forced upward through them. It is the chemical reaction of the hot blast of air, the burning coke, the iron ore, and the limestone that makes molten iron. About every 5 hours, workmen drill out a clay plug in the tap hole to drain off 250 tons of molten pig iron accumulated in the furnace hearth. Belching forth at 2,600 degrees, The liquid iron is so hot, it must be channeled in troughs made of heat-resistant clays. Workmen take a sample of each cast and send it to the modern laboratory, where it is quickly and accurately analyzed. Although high in iron quality, the product of the blast furnace is still not steel. It must be further refined to develop the properties required by the many uses of steel. As the next step, the molten iron is immediately taken to the open hearth department by diesel electric engines. And hot metal always has the right of way because much of the economy of making steel is dependent upon using the iron while it is still molten. At the open hearth building, the molten pig iron is poured from the hot metal car into a brick-lined ladle. This is transported by a huge crane, and the iron is charged directly into the open hearth furnaces. In addition to molten iron, the open hearths use scrap metal and other materials, such as raw iron ore and limestone. These are loaded into the furnace by this charging machine, which picks up each charging box as easily as though it were a spoon, thrusting it into the furnace and rotating it to spill its contents within. The entire charge is melted down under the heat of burners similar to blowtorches and held at a temperature of more than 3,000 degrees to refine the charge into high-quality steel. Samples are taken at intervals as workmen dip into the molten mass with long-handled spoons and pour the liquid metal into a sample mold. The sample is rushed by a pneumatic tube to the laboratory, where it is analyzed for various chemical components by expert laboratory technicians. If the sample report indicates that adjustments in the chemical content are needed, appropriate material is fed to the furnace by hand to bring it to the desired analysis. When a furnace is ready to be tapped, a clay plug in the back wall of the open hearth is burned out with an oxygen lance. With a rush of flame and sparks, the molten steel spurts out in a fiery stream and flows into the giant brick-lined ladle below. The glow of the molten steel and the shower of sparks make it a spectacular fireworks display. At each tapping, approximately 225 tons of steel are removed, steel equivalent to the amount used in more than 200 automobiles. In order to prevent them from being oxidized, most alloys are added as the steel flows into the ladle. So turbulent is the liquid metal that the alloys and other materials are evenly diffused by the mixing action in the ladle. The steel is then poured into ingot molds. It is allowed to cool just long enough to solidify before being transferred to a stripping crane. Here the molds are removed and the ingots, glowing red hot, are placed in soaking pits where they are uniformly reheated to approximately 2,400 degrees, making them malleable enough for rolling. Then the ingot is removed from the soaking pit and transported to the blooming mill in an electrically driven ingot buggy. Because an ingot is too large to be handled by the various rolling mills, it must first be rolled into blooms or slabs in this blooming mill. This mill is similar to a giant washing machine wringer that squeezes the ingot thinner and longer with each pass through the rolls. At times, it bites into the hot steel as much as 2 inches. Streams of water pour constantly over the rolls to keep them cool and prevent them from cracking. In order to control the width of the slab, the ingot is turned over mechanically at intervals. When the ingot has been rolled to the desired size, it is sent to a giant shear that cuts off the rough ends. The slab is then transferred to another furnace to be heated to a rolling temperature once more. In this long building, steel plate is rolled to fill the heavy demand in the West. The slab is pushed from the reheating furnace and carried on a roller table to the roughing stand of the plate mill, where it is reduced to an intermediate size. The roughly formed plate is then given successive back and forth rolling in this 3-high finishing mill until it emerges as finished plate. Workmen control these mills from a pulpit at one side by manipulating a series of levers and watching a huge dial which indicates thickness. It is an interesting sidelight that during the rolling process, the plate does not get any wider, but merely stretches longer and longer as it becomes thinner. High-pressure steam removes any scale that might hit the surface. When the big dial indicates that the plate is at the desired thickness, it is double-checked by a workman with a special hand gauge. After the plate has been leveled and the edges trimmed, it is marked and stamped to the customer's specifications, and powerful end shears cut the plate to its final size. It is then ready to be shipped to market, to be used in heavy construction, large pipelines, oil and water tanks. Starting with heavy plate, this modern 4-stand strip mill produces hot roll sheets and coils for heavy sheet metal work, storage tanks, pipes, auto frames, water heaters, and hundreds of other items. After the plate end is trimmed in a shear, it passes through 4 stands of rolls. Because each succeeding stand rolls it thinner and longer, the sheet emerges at speeds up to 20 miles per hour. At the structural mill, in another building, looms that have been heated to a rolling temperature of 2,300 degrees are passed back and forth through a series of rolling stands to make angles, channels, I-beams, and other shapes used for building and heavy construction. As the loom passes back and forth, it becomes longer and longer, and each time it is shifted to the next stand of rolls, it is gradually shaped into its final form. This steel will soon make many more buildings and bridges for the West. One of the spectacular operations in a steel mill is found in the merchant mill. Here the steel is rolled so thin and long that it must be threaded back and forth through a cross-country layout of rolling stands. These men grasp the hot ends with tongs and loop it around to the next stand of rolls. Note how they guide the steel by shifting their weight so that the force of the metal does the work. Reinforcing steel, rounds and squares, spring and auto bumper stock, plus flats for hundreds of other items are rolled here for use in our daily life. Cold-rolled steel, which is used by Western manufacturers to make articles ranging from furniture to electric irons, from furnace registers to adding machines and toys, is rolled in this mill. Coils that have first been pickled to remove scale are reduced to gauge by rolling back and forth, giving the steel an extremely smooth surface. Certain kinds of pipe are made from an intermediate product known as scalp, which is rolled from slabs that pass through a series of 10 stands of rolls. As the scalp passes through this mill, it becomes thinner and longer, and each succeeding roll stand must turn faster than the one before to take up the slack. Strip for the cold roll mill is also produced here. At the continuous weld pipe mill, where pipe from 1/2 to 4 inches is made, the scalp is uncoiled and fed into a machine that electrically welds the ends of each coil together, so that the scalp can be fed continuously into the pipe-making machine. This continuous ribbon of steel is first fed through a long furnace, where it is heated to more than 2,000 degrees, and the edges are raised nearly to the melting point. Emerging from the furnace, the steel passes through a set of forming rolls that bend it into circular pipe and press the near molten edges together. An air blast raises the temperature along the edge of the strip to a welding heat, and the edges are fused in the welding rolls. Succeeding rolls reduce the pipe to its approximate final diameter. A traveling saw, synchronized to move with the exact speed of the pipe, cuts it into convenient lengths to handle, even as it travels an average of 500 feet per minute. Enough pipe for an average 5-room house can be produced by this mill in 40 seconds. Larger pipe, ranging up to 12 3/4 inches in diameter, is made from steel scalp in the electric weld mill. The scalp is sandblasted and edge trimmed, after which it is shaped into circular pipe in a series of forming rolls. The edges are butted together and welded electrically to form a strong leak-proof seam. This weld is stronger than the steel itself. The weld is then cooled under streams of soluble oil, after which the pipe is straightened, tested, and shipped to be used for gas, oil, and water transmission. Basal Kaiser pipe, up to 30 inches in diameter for the oil and gas industries, is produced at Napa, California. Here, steel plate from Fontana is pickled in an acid bath to remove mill scale. Then a series of presses quickly and accurately give it cylindrical shape, beginning with this press, which bends the edges of the plate. A powerful ram pushes the plate down through side rolls that curl it into a U shape. It looks easy, but many thousands of tons of pressure are required. Accurate circular form is achieved in this hydraulically operated press, which compresses the plate between the upper and lower dies. This cold working of the steel, incidentally, changes the physical structure to give it additional strength to withstand the high internal pressures that are built up in oil and gas pipelines. Large circular electrodes conduct electricity, which heats the edges of the seam until they are near molten. Pressure rolls fuse the edges into a strong, true weld. After final inspection, the pipe is buffed and protected with a weather-resistant prime coating. And so today, Western pipe is moving in ever-increasing tonnage to markets once claimed by Eastern mills.